This is FE Peer Review. The date is the 17th of February 2022. Pablosdog wants to see the globe horizon. As most of you know, I'm caught up with some other projects at the moment, so I don't have much time to put into this. I'll have to keep this little video as streamlined as I can, but I couldn't resist just putting a little something out there. So let's take a look here. Pablosdog put up this image of one of the oil platforms off Santa Barbara and one of the islands in the distance, incredibly miraged and refracted. Arctic Reflections left a comment. What does this image prove other than that it was taken by a person who could not handle a camera? Pablosdog responded with, will we ever observe the globe horizon, parentheses, a physical obstruction versus an optical one, in front of platform C in the foreground, or at the 1,100-foot should-be location along the background ridges and mountains when observing the upper rigs? I mean, should it be possible given the right conditions, in your opinion? I responded, and I'm just going to read the last bit. You will practically never experience zero refraction conditions, so there will always be a bit of refraction to account for. But you can plan to minimize it. Then you can plan a series of observations at different heights. I'm going to address this in a response video. So there's a couple of issues here. First of all, you've got to accept that there's going to be always a little refraction, and so that's going to affect what we see. But that gets to the issue of, quote, a physical obstruction versus an optical one. So that's one thing we're going to address. And another thing we're going to address here is, yes, Pablosdog, if you want to see the globe horizon, you could actually see it. In fact, you've shown it in some of your pictures, but you still don't see it. But you could actually see it if you wanted to see it, simply by planning your observations better to reduce what are called confounding variables. And this is a standard problem in science. We're going to take a look at confounding variables. So that's the next thing. That's one of the things we're going to do in this video. And the last thing we're going to do is I'm going to pull back some of the images from the past. Ruhif has put together some nice ones that show very clearly that huge amounts of distant objects in Pablo's pictures are being obstructed. And not by mirages, but by the curved water surface. So Pablosdog, you've seen it. You've just closed your mind to it. Your eyes see it, but you don't let it enter your brain. I grabbed this quickly. It's a scientific paper published on the NCIB website. That's the government, the federal government's national health database of science, peer-reviewed science articles. And I grabbed it just because it has a good description of what confounding variables are. A confounder is a variable whose presence affects the variables being studied so that the results do not reflect the actual relationship. There are various ways to exclude or control confounding variables, including randomization, restriction, and matching. I should mention this article was written specifically with medical tests in mind, but the basic principles about confounding variables are applicable to all kinds of scientific experiments and observations. But all these methods are applicable at the time of the study design. So you need to design into your study how you're going to handle confounding variables. That means you have to identify the variables, you have to identify their anticipated effects, and you have to find ways to either quantify those effects so you can extract them out of your data, or find ways to eliminate them from entering into your data in the first place. That's called study design. So if you're going to design your study to reduce as much as possible these confounding variables, you're going to have to understand what those confounding variables are well enough to be able to quantify, to be able to develop techniques to reduce them as much as possible. Now, I've got a dozen or so articles and training manuals, and all from the US military, the telecommunications industry, papers on how radar works. I've got loads of papers on how to on how refraction works. A huge amount of work has been done on that, and a tremendous amount is known about it. I'll put all of those links, as I've done repeatedly in the past, in the description of this video, so that you, Pablosdog, can actually design your study to reduce or even perhaps eliminate some of these confounding variables. You'll have no excuse not to be able to. After you've read those papers, you'll know a lot about it. When experimental designs are premature, impractical, or impossible, researchers must rely on statistical methods to adjust for potentially confounding effects. So, best thing if you can avoid that altogether by simply excluding confounding variables to the maximum extent possible. So, confounding variables in your study, Pablosdog, are all of these heavily refracted and heavily miraged images. If you want to obtain information about refraction in mirages, well, then your photos are great. If you want to obtain information about the geometric reality of Earth, the physical geometry of Earth, then taking a bunch of pictures that are purposely as distorted as possible isn't the way to get there. You're actually emphasizing and introducing as much as possible confounding variables rather than trying to extract and eliminate them. So first thing, if you want to talk convincingly about the shape of the Earth based on your photography, stop wasting your time with all of these photos of mirages and refractions. I want to get back to this phrase that you used, Pablosdog, a physical obstruction versus an optical one. I made a point at the beginning of saying that the optical one is a physical obstruction, because what we are seeing, optical, is a real physical object. It's just that where we are seeing it is not a straight line between our eyes and where it actually is. We see it slightly elevated, typically, from where its actual location is, but it's a physical object. So it's a physical obstruction. And I'm going to demonstrate that with a few little simple diagrams here. Let's look at the top here. We've got a flat plane, and at the left we've got a gray square, which is our observer. In the middle there's a yellow circle, which is some object. Could be a coin on a table, it could be a lighthouse on the water. At the right there's an orange pentagon. Again, could be anything. Could be an island. The yellow could be an oil rig. This could be you at UC Santa Barbara. If the Earth were flat, and if this was a flat plane you were on, and if there was no atmosphere, then light would be traveling in straight lines from the object to your eyes, and from the object to your eyes, straight lines. Fortunately, there is an atmosphere, and we've got air to breathe, and consequently, that light is going to take a very slightly curved path. So I've swapped out the straight lines for a couple of very slightly curved lines. And when you're talking about atmospheric refraction over these long distances, especially under low and moderate conditions, it really is only very, very slightly curved. We're talking about a fraction of a percent off of a straight line deviation we're talking about. So if your light coming off of your platform here, we'll call this platform C, if that light was coming to you in a very slightly curved line, you would be seeing it slightly higher than it actually is physically. And if your orange pentagon over here, perhaps it's one of the other platforms, or perhaps it's one of the islands in the distance, if that light were coming to your eyes, it would be following the same degree of curvature. We're talking about low to moderate refraction conditions that are consistent across the whole space here. Under those kind of conditions, it would follow the same degree of curvature, that arc, and consequently would appear higher than the object in the middle, even though, as I've drawn it, it's approximately the same size and is on the same plane. So you would be, if you were on a flat Earth with an atmosphere, you would be seeing the closer object below and the more distant object above. And the farther out the objects are, the higher up they would appear. Of course, eventually the vapor, water vapor in the atmosphere and all, would cause everything to just sort of disappear into a distant mist. There would be no horizon at all. The effect you'd be seeing, because it's not just the objects on the surface that are reflecting light towards you, it's the surface itself. This entire surface is reflecting light towards your eye. The effect you would be seeing is that this curved upward. It would look as if the Earth was concave. A flat Earth with an atmosphere would appear concave, and there'd be no horizon. Things would just simply disappear into a very distant mist. I don't mean a physical mist, but like a misty effect in the sky. Now let's look at what happens when we introduce a curved surface. We're going to start with light traveling in straight lines, no atmosphere, same three objects, same distance apart. The middle object is seen by the observer. The distant object is obscured by the curved Earth's surface here. So the distant object, in this case, that dotted line there being the straight line, is cut off right here. And so it's not seen by the observer. So that's the effect we talk about with things disappearing below the horizon. But this diagram, of course, shows with straight lines, not with an atmosphere and with refraction. Now we'll look at that next. So here we see curved Earth with refraction, with an atmosphere. The closer object, the light comes in at a slight angle, so consequently where it appears to us, where it appears is up here a little bit. The more distant object now remains visible above the horizon because the path of the light is curved just enough to clear the horizon. Note one more thing though. The light coming off the bottom of the distant object does not clear the horizon. So in this case, as I've drawn it here, and yeah, this is not to scale, not to any particular scale, but as I've drawn it, the bottom of the object is not visible to our observer. It's obstructed right here, where that dotted line crosses that thick black line. That's about right there. So that spot there, where this is obstructed, is going to be where we see a horizon. It's going to be the spot of water that's blocking this object. And it's a physical spot. And we see it, so it's optical too. But we wouldn't even see it if it didn't exist. It can only be optical if it's also physical. And it's physical and we see it. Now again, remember that all of this water surface is also reflecting light. So we're seeing light coming off of this entire surface here all the way up to this point. And the light ray that's coming off of this point is just skirting the water surface and reaching our eyes. Beyond that, the light over here, the water over here, beyond that, is not reaching our eyes. We're not seeing the light coming off that surface. These simple diagrams should make it abundantly clear that on a flat Earth, you would see a concave surface with atmospheric refraction and no horizon. And on an Earth with curvature, you would see a horizon. It would simply be a little farther out than the straight line path from your eyes to the tangent of the Earth's surface. Because the light would not be traveling in a straight line, it would be coming to you slightly curved. Really not very complicated, all of this. Before we move on, I want to say one more thing about this refraction issue. Upward refraction is not a thing. It's a condition that occurs very, very rarely. It's not something you're going to go out and photograph day after day after day. Am I making a claim here? I'll tell you this. Pablosdog, you read the 12 scientific papers, training manuals, and articles that are in the description. You disprove the science in all of them. You then publish that in a peer-reviewed journal and get all those organizations which are using all that wrong information that you've disproven to change their training manuals and their scientific papers and their design parameters for their missile systems and radar systems. You get them to do all of that based on your new science of refraction, and you'll have a case to make. Until then, you just simply don't. So no, upward refraction is not the escape route here. Okay, let's move on to the next subject. Here we are looking at Google Earth, and we've got Platform C over here on the right. We've got the UCSB parking lot here on the left. And you asked in your comment, will we ever observe the globe horizon in front of Platform C in the foreground? I mean, it should be possible given the right conditions. Well, yes, so if you'd like to see it, Pablosdog, this is how you would do it. For a start, you would not do it on a day when there's lots of refraction and lots of miraging. You will design your observation on a day where refraction is likely to be least, minimal, lowest, smallest amount of refraction. And my understanding, the best kind of conditions for that are first half of the day, a cool day, cloudy, but not ground fog, of course, but a good cloud cover keeps the air cool, keeps everything near the water temperature. Conditions like that in the first half of the day are generally going to have the best conditions for low refraction. And then what you do, if you want to see this globe curvature and the obstruction, is you do observations at different elevations above the water line. So let's go over to your favorite UCSB parking lot here, which is at roughly 45 feet above sea level. It's a fine spot to do an observation from. And then you know what you can do is you can go down to the end of the parking lot, and there's a staircase that goes down towards the beach. And if you go down to one of these landings on the staircase, that'd put you about, 10 or 15 feet above the water surface. That'd be a good spot for another observation. I would not recommend going right down to the edge of the water and putting your camera right there at the edge of the water like so many flat earthers like to do. When you get that close to the water surface, even under the best conditions, you're liable to get a lot of refraction again. So that's just a cop-out, that approach. But this stair landing here would be great. And then that would put you at about 10 or 15 feet above. Here you're at about 45 above. Ideally, you'd go higher still. I don't know, there's no high ground in the Santa Barbara campus that I can find. I don't know if you can get up into the upper floors of any of these buildings or even onto a roof. If you can, that would be convenient because it would be very close by. If you can't, you don't have far to go. 2.5 miles away, the More Mesa here has footpaths that go out, and I believe that you could just set yourself up at one of these points. You'd only be about 2.5 miles from your original observation. Your elevation here is at around 110, according to the elevations on Google Earth, and you'd have a good clear line of sight to those same landmarks you were looking at. So there you go, 10 to 15 feet above the water, 45 feet above the water, 110 feet above the water. A good clear line of sight to Platform C and also to the islands. Compare the three results you get from those three elevations. Try to take them as close as you can in time so that conditions haven't changed much. Compare the differences you get in elevation there with what is calculated for Earth curvature using moderate to low refraction, and see if it matches. You got the guts to do that? You got the nerve to do that? You ready to pull your head out of the sand like that ostrich over there with his head in sand? Take a look around at the world around you? It's not my job to pull your head out of the sand. That's the thing you've got to do. I might be able to give that ostrich a little kick in the bum, and that might shock it enough. But you're the one that's got to get your head out of the sand. Your own photos, again and again, when you do a few that are relatively low refraction conditions, show clearly Earth curvature. Last December, I did a video analyzing one of your images and showed that the shoreline over at La Conchita is down that far below the water. This image had a very, very slight bit of mirage in it. Not a whole lot of refraction, a little bit of mirage. And that shoreline across there that we're not seeing is all the way down at the bottom of this red line. So about a little over 2 weeks back, Pablosdog, you put up this photograph that you took of the hillside there and La Conchita in the distance. And you asked the question, where's 45-foot elevation? I poked around a little bit and found some good topographic maps of the area and determined that 45 feet was roughly where I've got the mouse. And then I looked at the distant hillside. Well, your observation point was at 45 feet, and this part of the hill was at 45 feet, so straight ahead of you there. And that, on a flat earth, that distant hillside should also be 45 feet. Well, it was easy enough to figure out what it was, and it was not 45 feet. We have these nice distinct features we can recognize here. And I found that that same line there was about 235 feet. So, a little bit of geometry that completely falls flat on its face, on a flat earth, and a little bit of geometry that works perfectly fine with the globe earth, exactly as expected. This happened to be moderate to high, be close to high level reflection, not high, not particularly high. And it was your photo and your question, and it's right there in front of us, Earth curvature. So what's this down here? This is the horizon. This is the water, and it's blocking the view of La Conchita. We don't see La Conchita. We're missing about 50 feet of ground surface on that distant hill there. All right, let's take a look at one more. Ruhif has done multiple videos analyzing your stuff, and here he's showing that the bottom of these mountains here is down here. We've shown you again and again from your own imagery that you're seeing Earth curvature. You just can't bear to admit it to yourself. Take a look at these 4 oil rigs here, C, B, A, and I think, is this Habitat? I've forgotten which one this is. We see the substructure, we see a little less of the substructure, we see even less, and then finally we don't see any at all. What do you know? And mind you, if you got a decent shot of this view on a day when refraction is low and conditions are ideal, then you'd really have something to work with. But you just don't have the guts to do it, Pablosdog. You just want to make your claims about a curved earth and get all those little back pats from all your fellow flat earthers, flatzoids, saying, "You're a good boy, Pablosdog. You're a good boy. Good doggy." It's really pitiful. I don't know why I spend any time on this at all. Good luck in life, Pablosdog. I think I'm finished with your work here. There's really nothing left to it. It's been chewed up and spit out like a piece of old tobacco. All right, folks, that's it. I took too much time on this, and I've got other work to do, so I'll try not to get sucked in again. I've got a few things to do the next few weeks, and I will be traveling as well, so don't expect to hear much from me. Bye now.